Hello, everyone. Before we get started, I need to remind everyone to turn off their phone, and please kindly fill up the survey at the end when you receive the email. Okay, so bonjour, hi. Today I'm very excited to talk to you about turning a photo of a person to a 3D mesh with a rig for games. My name is Nghiep, and a technical art director. In the past, I was a teacher and worked on many games at different companies. My co-author is Hector Leon, a research engineer, and we are currently at EA in the SEED team. SEED is an acronym for Search for Extraordinary Experiences Division, which is an applied research and innovation group where we explore, build, and help define the future of interactive entertainment. Here's today's agenda, where I will explain our different projects and how they are combined together to go from a single photo to a facial rig. Starting from an input image, it reconstructs an avatar, refines it, finds its expressions, and puts it onto a rig. So this is the full pipeline that will be presented, but don't worry, it will be shown in chunks to better explain each part of the process. So let's get started with a bit of introduction into the field and what we're trying to improve. So imagine that you are working on a project that requires 10 to 20 main characters, and each character needs a face that can show various emotions and expressions. Creating each of these face rigs can take weeks or even months to complete. And that's because there are so many details that go into animating a realistic face, like capturing different expressions, eye movements, and facial features. For larger projects, you might also have secondary characters, friends, family members, or background characters. They still need expressive faces, of course, but to save time and resources, they may have fewer and simpler expressions. However, if not done carefully, this can make the animation seem less immersive. And when it comes to creating a facial rig that can accommodate a wide range of identities, there are several challenges to consider. You see, each person has unique facial features, which means that a one-size-fits-all approach simply won't work. The example here are courtesy from Trippelgangers. And as you can see, different people have different skin tones, nose, eyes, lips, as well as facial proportions and structures. Capturing all these variations can be a daunting task. And when it comes to representing different races, genders, and ages, the difficulty becomes even more significant. Another challenge in facial rigging is capturing the diversity of expressions that people make. After all, our faces are incredibly expressive, and there are countless ways that we convey emotions and reactions. And of course, there's yet another challenge in facial rigging, which is the diversity of controls that can be used to animate the expressions. So all our internal solutions presented today are rig agnostic. So it can work on any of these rigs. But for simplicity's sake, I will demo only on our internal facial rigging solution created by the tools and tech team called FaceRig. So the process will not create a new rig every time. Instead, it will use a reference rig to optimize and replace existing blend shapes so that the animations can be later shared between characters. And now, this is very important for game projects to save time and space, as well as support face customization. Now that I've given enough context, where do we start? With data, of course. So I will go over what kind of data and how it is processed. Here's the full pipeline again. So let's concentrate on the foundation, the data, and specifically expression scans, which could be captured in many different ways. In the next few examples, we scan our old colleague Jörg Schweller. And there's a few requirements. The data must have a consistent topology and stabilized. We used Mathieu Lamar's implementation as shown here. The next part can be summarized into 3. Ideally, all 3 parts are iterated together, but this is not always the case in production. So an artist will decompose the expression scans into their isolated blend shapes. The blend shapes must be ensured that they are playing properly with the rig controls, and that it can also be intuitively animated. All this is done iteratively by different people on the team. And to accelerate the pipeline, we will use instead a process internally called FaceOptim to do this loop automatically. Of course, the user can always edit the output later on. FaceOptim uses rig inversion to estimate the rig controls animation so it can solve the blend shapes. Please take a look at our paper provided here for information. So going back to the pipeline, FaceOptim is launched right after the cleanup of the scans. And in this example, 44 discrete expressions plus the neutral are used, but any number can work. And I've tried it myself with 2 expressions, and results still work pretty well. The process is launched to one of our servers, and here's the result in Maya. The rig controls are solved for every input expressions, and you can still modify anything. The rig acts like a regularizer, which constrains the shape region and expressiveness. This is very obvious around the ears and chest region. I'll let you appreciate a bit the animation. So I did mention that any number of scans can work. So what about continuous motion? If you can afford higher quality as well as able to capture and process 4D animation data, the requirements are the same as before. The data must have a consistent topology and stabilized. We used the tracking solution from Mathieu Lamar as shown here. And here's the result. So FaceOptim is using the full 10,000 frames for the solve, where it optimized the blend shapes and animated the rig controls. So notice the fat and muscles are well maintained, but is of course dependent on the flexibility of the rig. As shown here, you can still modify the animation using the rig as shown before. That should be the last awkward silence. On the other hand, if you don't want to scan or sculpt a full set of expressions, what could the solution be? So let's go back to the pipeline flowchart. It would be reasonable to think that with all the scans that were already processed, be put into a database. And in turn, that database be used to generate the blend shape for the rig later on. That tool is internally called FaceMixer. With a single neutral, it will infer the best blend shapes. And we've set up a web service to enable anyone at EA to test and use it on their project, as well as an API call for direct use in Maya or other DCCs, and GitLab source code access. In the next example, I will demonstrate its usage with a web service. FaceMixer requires a neutral mesh that uses our universal face topology. Once the user has navigated to the FaceMixer webpage, they can input that OBJ file into the field. The web service was made by my colleague, Etienne Danvois. Then the user selects the database that they want, click on Submit, and wait a minute or two. The service will return a zip file with all the generated blend shapes. So how does FaceMixer work? We have a database of 59 different faces with around 467 blend shapes, which were generated using FaceOptim, as well as 9 region masks to help the optimization process. For each region mask, we find the best identity in the database as a weighted number and apply their contribution for each blend shapes. Here's the result in Maya for a new head that is not in the database. So the quality result will vary depending on the diversity of the database. In this case, the results are mediocre, since we do not have many samples of face with this morphology, and of course, 59 heads in the database is quite small. By now, you're probably wondering how FaceMixer and FaceOptim compare in terms of quality. So I've chosen a few frames with the main differences highlighted here. So notice the lips, the chin, the jaw regions are, of course, better on FaceOptim. Here, mostly the corner of the lips. This shape works well enough in both cases. And FaceMixer had a really hard time on this one. Now that the blend shapes and the rig part is done, let's move on to the other part. So here's what's been shown before. What comes next is a tool called Facebot. It's a process that can generate and upres a face using numbers, or using a mesh with or without textures. The first part is a preview mode, where it will generate meshes, diffuse, and norm map from a latent space. The textures are generated at 512, and the meshes at 9,000 vertices, and runs not really real time, but almost. The second part is meant to increase the resolution of textures from 512 to 2K. A diffusion image-to-image method is used to upres them automatically. Same thing for the norm map. However, when applied together for rendering, the results are not photoreal. So how do we increase the realism? We can use another image-to-image translation method, but this isn't really usable for real-time, as it takes a few seconds to generate each images. So we will optimize the data for our traditional rendering pipeline by using the image-to-image as a reference. To do so, we'll use differentiable rendering. And of course, if you can do it on one, then you can do it on many. The example shown here is the interpolation between random latent numbers. The generated data also works under different lighting conditions, since the textures are PBR. Hopefully by now you're dying to know how this is done. So let's go over how Facebot is able to convert the references to real-time compatible data meant for games. Inspired by traditional computer vision techniques, it will simulate photometric stereo and photogrammetry by varying the lights and camera positions, which will then be used for our optimization process. Here's the light position that were used for the process, manually placed in Blender, and the camera positions. Here's an image of image translation from different pair of lights and camera combinations. Notice how the identity is not maintained properly during the translation process. So we need different strategies to reduce this noise. One of which is to use perceptual loss at the last epoch. The optimization is also done in a coarse to fine manner. Notice how the lips are slowly closing to match the reference. We solve for the mesh and textures, but subsurface scattering is not taken into account. The initial state on the left is the previous diffusion process that upscaled the texture from 512 to 2K, and on the right, after it was optimized. Same for the roughness map and the norm map. You might be wondering now, where does the input photo come into play? Since Facebot does not take photos directly, a mesh and diffuse must be generated first. The next part is a project from Hector Leon, and I will present his section on his behalf. So here's the pipeline so far. The next process is photo to mesh, called Maria. So what is Maria? Maria is a consumer-level avatar acquisition system. It receives as input a single picture from a consumer device, and it outputs a mesh and a texture. This avatar is represented with numbers. We use what is called a morphable model, shown here, that uses dimensionality reduction, PCA in this case, to represent the mesh and textures with parameters. It allows us to use matrix multiplication to obtain the final avatar, which works nicely with ML algorithms. Maria is an optimization algorithm. What this system optimizes are the avatar parameters that we've just talked about. It also optimizes other rendering parameters like camera position and field of view. So given a target image with an initial set of parameters, the goal is to optimize these parameters until the avatar looks like the input image. Hector uses a differentiable render to match the avatar to the target image, among other modules like landmark detector and a face encoder that extracts facial features. Here are some reconstructions. The left column is the input image. The middle one is the avatar overlaid over the image, and the right one is the generated avatar. Now, let's see how we take the generated avatar and make them more photoreal. We'll now combine Hector's project and my own. So let's go back to the flowchart and where we are. So let's go over what it implies. Given an image, we use Maria to obtain a coarse mesh and an initial diffuse texture of 512. Then we use Facebot to upres the diffuse texture, generate a norm map and roughness map to 2K by 2K. It is then optimized to get a photoreal look. Up next. One of the missing pieces were the eyes. Luckily, Mathieu Lamarre and Shubham Chopra were working on an automated fitting process, and we asked to place the eyes using the photo. Sorry, I'm just gonna. So here's an example, including the eye fitting, and also when the lighting isn't optimal. And the video showed the step-by-step. A few more examples on different photos to show that it can work on any identities. What about animation? There are different ways to generate the blend shapes for the rig to animate, but the quickest route is to use Face Mixer. With the previous example as the input, here's the result of Face Mixer in Maya. Since there's no wrinkle map on this preview scene, the corner of the mouth's unchanging norm map looks a bit weird. Also, the quality is very dependent on our database, and to improve it, we'll have to use our better data in the near future. The second option is using Facebot, since it's also trained to generate the expressions similar to the ones scanned in the first few slides. To do so, a simplified deformation field is sent to Facebot with the identity of the person. In this case, it was a randomly generated head from Facebot. And a few hours later, the mesh and textures are all generated for each expression from the deformation data. It can then be sent to FaceOptim. But this is not the normal pipeline when we serve the users, since the generation time is very long. Which comes to our last question of how can we best serve the users? So if you've worked with Python before, you've probably had the challenge of trying to deploy packages to users. It would be possible to have the user install all the required packages and use all their VRAM and CPU processing power, which would completely stop them from doing any kind of work. So instead, we adopted the same philosophy as Face Mixer and use a web interface for the user. The required input is an image. There's no hard constraint, as long as one face is there. The user inputs it on the web page, courtesy of Etienne, clicks on Submit. It will upload. If the user has provided many identities, then they will be launched in parallel on the form computers. When they come back, they click on View History, where the results are ready. Click on Download, and a zip file will be created. Here are the result textures and the preview video, as well as the mesh on the rig as a Maya file. I was also curious to compare the real scans that was made versus the hallucinated mesh from the process. As expected, it's not even close. So we need to improve our algorithms and dataset. However, the seed has been planted for future work. In conclusion, I'd like to thank our other team members for their help and support. And that's it. I'm open for a question. I think my throat is about to die, so let's not do it too long.
Hi, I wanted to ask about Facebot. What exactly are you, maybe you explained it, but I'm not sure.
Okay.
How exactly are you generating diffuse maps and normal maps? Are you using a sort of stable diffusion or something similar?
Yeah, so Facebot has multiple modules. And it's basically a neural network that was trained on different data sets that already has diffuse and norm map.
So it's your own proprietary network?
Yeah. We also source our own data set, and we also bought some. Does that answer your question?
Yes, thank you.
Okay, thank you.
Hi there, I'll have a question. In the beginning of the talk, you mentioned you have like a web service for uploading faces to apply blend shapes to those. And I'm just curious, earlier you also said that you had like they had to have the same like number of polygons and the same like mesh ordering. How do you kind of like ensure that your artists upload the correct mesh that works with the system?
Yeah, so the question is how do we enforce proper data on the web service? Yeah. Well, we don't really. We make the assumption that people know the limitations. So the only thing that we check is it exactly that amount of vertex?
And do you like distribute a base face to art teams to use to build against the system?
Yeah, so for many years there was a push to use a universal face topology. So with varying success. So we are just hoping that people are using the right one.
The hope and pray method.
Yeah.
That's amazing.
Very much.
Anyway, it's very incredible work. Thank you so much.
Thank you. All right. Good. Okay. Well, if there's no more any questions, we can probably stop here. Thank you very much.